Hey guys, hope you're well. So today I'm going to talk about this process to design an observer and controller in state space called Ackermann's formula. Um, the general, so the problem that we're going to be considering today is given a linear time invariant system, and remember a linear time invariant system is x dot is equal to ax plus bu, and then we have an output equal to cx. Okay. And so the problem is, given this system, x equal to ax plus bu and y equal to cx, how do we design a controller if the full state is unknown? So we can observe and we can only measure and observe u and y. How do we reconstruct the state to then provide us enough details that we can design a controller around to then inject into our system to drive the process that we want to drive? And so this is where the idea of state estimation comes in, or state observer design. So what we're going to do is we're going to essentially take a copy of our system, because we know what our system is. We know our A, we know our B, and we know our C, right? Those are known quantities. We're gonna take those knowns, and we're going to say, okay, well, let's make a copy of that, and we're going to use this notation x hat as our estimate. And we're going to say our estimate is equal to a copy of our system with also with the input that's known. Okay. And then we're going to also make a copy of the output, y hat is equal to cx. However, we're going to add an extra term over here. We're going to add this L plus y minus y hat. Okay, so now as we're going to measure our system, and we're going to take the measurement of our what's called a state estimator. And we're going to compare those two values. And as those two values converge together, we're going to show that our estimate actually converges to the actual state under the assumption that our system is observable. This is why looking at those quantities before, the observability Gramian and the controllability Gramian are useful before actually entering this phase of the design. So it makes an easy check. So what this looks like, if we draw out the phase or the block diagram here, we'll have our system here, our LTI system. So this will be, let me go do this way. So this will be x dot is equal to ax plus bu, and then we'll get y is equal to c times x. Draw a box around this. Okay. And then we're going to take the output of that. We got this goes into an input. Okay, so then we're going to take this output, and we're going to see what's the best way to do this. Drop it down, and then this is going to go in this direction and into a new block diagram with our estimate here. X dot is equal to ax hat plus bu, and y actually, and then that's the output of this system. So let me move this down here, replace that dot. Great. Draw a box around that. Okay, so then we have to take the output, a line from the output, and also make that go into the input there. And now we can take this output, which is x hat now, x hat. Maybe that's the way to go. There we go. So let's see, what do we have here? We have u, we have y. Now we can design a controller, let's say k, to compare our reference with our state estimate. And then this will go into our will go into our system here. So this is our error. It's equal to our reference minus our estimate here. Instead of our state here, now it's our estimate. Okay. Awesome. So this is what a typical block diagram would look like with your observer and your control system design. Okay. So now what? Why is this useful or interesting? So let's see here. With the observer and our regular system, we can define a new quantity. Okay. E, oops, let's move this down a little bit. Lost line. There we go. E, which we're going to say equals our x minus x hat. Okay, so this is the error. This is the error of our between our state and our estimate, and we want to show that this is convergent to something. Okay, what is that something? Okay, so let's take the derivative of our error. So that'll be equal to the derivative of our state minus the derivative of our estimate. Okay, so then this is going to go into ax plus bu minus ax hat plus bu plus l y minus y hat. So then this is going to be equal to, again, ax plus bu minus a hat plus, oops, minus bu minus l. Y is equal to c times x. Y hat is equal to c times x hat times x hat. All right, and so now let's look at this. So this cancels out with this. And then we get this following. We get the following. We get a times x minus x hat minus l c x minus x hat, which is equal to a l c x minus x hat, which finally is equal to a l c times e. So now our error system is equal to E dot is equal to A L C times E. Okay, so now what properties would this have to satisfy to ensure that E goes to 0, right? Well, we just need asymptotic stability. Okay, so if we can show that our system is asymptotically stable, then we know that our estimate will converge to our state. That results in having to design L such that this holds. Okay, so essentially we need to, just like with the controller design that I showed earlier, when I started introducing state space design, we had to define K such that the controller converges to our reference. So now we have to pick L such that our observer or state estimator goes to forces E to converge to 0. So that's pretty neat. Now what happens when we have our K in there as well? So let's note that with the proposed controller, state equations become x dot is equal to ax plus b times r minus x hat. Right, so if we go back up here, we get that our u is equal to k times e. Should I see? Or r should be, let me make sure that I do this right. Yeah, so there should be a k, not up here. Let me change this really fast. So this will go through there, and then we have our k as being multiplied by our x hat for this example. Okay, so now, so we fixed that. Now we have that. So this implies, oops, where's my drawer? There we go. All right, so now this leads to x dot is equal to ax plus b r minus k hat plus, and then we're just going to add in, subtract in our bkx minus bkx. And then we're going to split up everything. So we get a minus bk x plus bk times e, the error, plus br. So now if we take our state, take our state as, let's do chi is equal to x and x hat, or x and e, sorry, where again, our x is equal to x dot is equal to a minus bk x plus bk e plus br, and then our e dot is equal to a minus lc e, and we take the stack of this and put it into a single state. This is going to be, again, dot. This will be equal to x dot and e dot, which is equal to the block matrix a minus bk, 0, a minus lc, plus b 0 times r. All right, so now what we can do is if we want to show that this system here is asymptotically stable, that resolves to just ensuring that the eigenvalues are less than 0, right? So what we can do is we can show that that's true if we note that this is a upper triangular matrix, right? So that means that the determinant of this guy, which you would use to find your eigenvalues, can be separated. So this is due to the separation principle. And the structure of, let's call this matrix A tilde, and the structure of A tilde, it follows that the determinant of A tilde is equal to the determinant of the diagonals separately. All right, so and actually you can show this pretty easily, right? So if you wanted the determinant of this matrix A, you can choose which direction you go, but you can choose it's this guy times this guy, the determinant of this guy times this guy minus the determinant of this guy times this guy. This is 0, so it resolves to be to show that you just need to find the determinant of the 1, 1 element and the 2, 2 element, and then the combined is the determinant of the full thing. So that's pretty neat. So we just showed that we can essentially design our controller and observer separately and independently from each other, which is really powerful. And so there's under this assumption of linear time invariant systems, we can actually decouple the designs for both of them.